Now, we will be talking about organic compounds which contain oxygen. The oxygen containing organic compounds play a very important role in different compounds, and the speciality of the oxygen containing compound is it is a very versatile, important synthetic material too. The oxygen compounds are normally classified as to belong to two classes. One, those in where the carbon is bonded to the oxygen by a single bond. For example, alcohols, phenols and ethers. The other set is where the oxygen is bonded to the carbon atom by a double bond. They are aldehydes, ketones and carboxylic acids and their derivatives. So, these are the two important classes of organic compounds which contain oxygen. When we talk about oxygen containing compound, it is better for us, good for us to know and understand a small introduction into oxygen. Oxygen, all of us know, has an atomic number of 8, its mass number is 16. When you see the electronic configuration of an oxygen atom, we find that the electrons are like this: 1s2, 2s2 and 2p, you got 4 electrons. The valence shell is here the L shell. Here there are 2 electrons in the 2s, they are paired, and in the 3 2p orbitals you find that in px there are 2 electrons, they are paired, and in py and pz you got 1 electron each. So, in the valence shell, the L shell, we find that there are 2 pairs of electrons which are not going to be active for bond formation, they are called as the non-bonded pairs of electrons, and there are 2 unpaired electrons and these are called as the bonding electrons. So, oxygen has 2 non-bonded pairs of electrons and 2 bonding electrons. It implies that oxygen can form 2 bonds. When you compare carbon and oxygen in the hybridized state, we find that carbon, each of the sp3 hybridized orbital has 1 electron each, and it is a classical sp3 hybridized carbon where the 4 orbitals are pointing towards the 4 corners of a tetrahedron, and the angle between any 2 orbital will be exactly 109 degree 28 minutes. Here each orbital has only 1 electron, so it is can be considered to be a perfectly symmetrical arrangement. But when you check here, there is an interesting thing. When you look at the electronic configuration, you find that the 2 unpaired electrons are in the px and py or py or pz. So, they are mutually perpendicular. So, the angle between them should be 90 degrees. But in almost all organic compounds or all inorganic compounds too, the oxygen's bond length angle is not 90 degree. It is here that we need to talk about hybridization. Just like carbon, oxygen can also undergo hybridization. The 2s and 2p orbitals are involved in the hybridization. So, just like in carbon, it undergoes either sp3 or sp2 hybridization. Here, when the hybridization takes place, we get 4 degenerate sp3 hybrid orbitals, and in these 4 degenerate set of hybrid orbitals, we need to fill 6 electrons, and we can find that you have in one sp3 orbital you got 2 electrons, the other sp3 you got 2 electrons, and the other remaining 2 have got 1 unpaired electron each. So, just like in the ground state, the net position of the unpaired electron remains same, but an interesting change has taken place. Here the sp3 hybridized orbitals are at an angle of 109 degree 28 minutes, and in the case of carbon, the 109 degree 28 minutes was classical because each orbital had 1 electron each. When you check the electronic configuration of the hybridized oxygen atom, you find that the 2 orbitals have 2 electrons each, and the remaining 2 orbitals have got 1 unpaired electrons. So, the electron density on one plane due to the presence of 2 non-bonded pairs of electrons is so large. This results in what? A compression of the bond angle in the case of oxygen. So, in carbon all the angles are exactly 109 degree 28 minutes, but here the case is different because the electron density is different. So, this is an interesting difference between carbon and oxygen. the sp3 hybridized state. Now, when we examine a molecule of water, we find that the bonding electrons which results in the formation of the two OH bonds of water, the HOH bond, the bond angle on measurement is found to be 105 degree. Why it is 105 degree and not 109 degree 28 minutes, just like in the case of carbon? Because it is sp3, it should have been 109 degree 28 minutes. Here again we go for the same reason. The non-bonded pair electron and the bond pair electron, there is a repulsion. So, what should have been 109 degree gets compressed and comes down to 105 degree. When we examine an alcohol, in an alcohol we can say that it is an alkyl substitute to water, that is one of the bonds H is replaced by an alkyl part. Now, alkyl groups are bulkier groups. So, the non-bond pair repulsion is lesser, because the bulkier atom alkyl group cannot be compressed as much as that of a small atom like hydrogen. So, the angle on measurement is found to be 108, around 108 degrees. When you talk about phenol, the alkyl is now substituted by benzene ring. Benzene rings are still more bulkier. So, compression is lesser to a lesser extent, and it is almost 109 degree. When we examine ether, what is ether actually? In water we have got HOH, here in ether the 2H of water can be said to be replaced by 2 alkyl parts, alkyl groups. Now, alkyl groups on both ends are bulky groups. Here there is a new phenomenon, that is the bond pair, there is alkyl groups repel among themselves and the bond angle is increased. The bond angle increases to 111 degree. So, this is an important feature of the sp3 hybridized oxygen atoms bond angle. So, you must be very clear with it, that is the bond angle should have been 109 degree 28 minutes, but it is not so because of the compression due to lone pair bond pair repulsion. Okay. Another interesting thing that you must know is, in a molecule of alcohol, you have got ROH. Water molecule exists as a liquid. Why? Because of hydrogen bond. Because whenever an electronegative atom is bonded to an hydrogen atom is bonded to an electronegative atom, the bond becomes polar, it becomes delta minus and delta plus. Such a delta plus H, when it comes in close to some other electronegative atom, there is a small weak force of attraction, and this weak force of attraction is called as the hydrogen bond. The same thing applies in the case of alcohol. In alcohol, you got ROH. Here there is an OH bond. The OH bond is polar. It will be delta minus and delta plus. When similarly another alcohol molecule comes close to this molecule, there is a weak force of attraction between the delta H plus and the electronegative atom, the oxygen of the next alcohol molecule. So, what happens? These molecules now become closer to each other. They are packed closer to each other. Once they come closer to each other, it exists in the form of liquid. So, an interesting thing is, why does alcohol exist as liquids? Because of the hydrogen bonding. Another interesting feature is solubility of the lower alcohols in water. Why are lower alcohols soluble in water? Because the alcohol's OH bond, which is polar, the delta H plus can form a hydrogen bond with water molecule. So, this water molecule and alcohol molecules easily form hydrogen bond, and therefore, we say that find that almost lower alcohols are soluble in water. Higher alcohols, where the alkyl group increases bit C4, C5, etc., then the hydrophobic part is larger, therefore, it is less soluble in water. So, this is also an interesting thing. So, these are things that you must always remember in the case of alcohol. Another interesting feature that you must understand is the alcohol's OH group's nature. Now, alcohol molecule is ROH, oxygen has 2 non-bonded pairs of electrons. Okay. The OH bond is polar, and if possible, it can break. How can it break? It can break as RO minus, alkoxide anion, and the H plus. So, alcohol can release H plus. So, the question is whether alcohols can show this acidic property, that is, can it release H plus ion. When we examine the case of an alcohol, let us take the example of an ethanol. Ethanol is CH3CH2OH. If the OH bond breaks, what do we get? CH3CH2O minus and H plus goes off. Oxygen already has 2 non-bonded pairs of electrons. And now a negative charge also comes and resides on the oxygen atom. So, the electron density around the oxygen atom increases. Now, in addition to it, you have got an alkyl group, that is a CH3CH2 group. CH3CH2 groups are electron releasing or electron donating plus I group. What does it do? It will further increase the electron density in the oxygen atom. Now, what happens then, and then the oxygen now has tremendous negative character, and this will make the oxygen atom highly unstable. So, in net we can say the alkoxide anion is highly unstable because of the plus I effect of the alkyl group. If the alkyl group was electron withdrawing, or if it could take up the electrons of the oxygen, excess electrons of the oxygen, it would have stabilized the alkoxide anion. Here it is not so. Therefore, alkoxide anion is unstable. Therefore, alcohol generally do not release H plus spontaneously. Okay. And when you compare it with water, alcohol is ROH, water is HOH. Alkyl groups are electron donating groups. So, the alkoxide anion is unstable. Water, at least it is H. H does not give electrons or take electrons. Therefore, the anion HO minus, the conjugate base that is formed, is more stable in the case of water than in the case of alcohol. Therefore, water molecule is said to be slightly more acidic than alcohols. A small exception, always remember, methanol is the only alcohol which is more acidic than water. All other alcohols are less acidic than water molecule. So, this is an interesting thing that you must also understand. Now, let us talk about the properties of alcohols. Alcohols belong to 3 categories. They are primary alcohols, secondary alcohols and tertiary alcohols. Just like in the case of haloalkanes, here from the name we can differentiate the whether it belongs to the primary alcohol category or the secondary alcohol category or the tertiary alcohol category. Primary alcohols will always end with as 1-ol. It can be butane 1-ol, it can be propane 1-ol, it can be pentane 1-ol, etc. It will be 1-ol, it will be at the end carbon. A secondary alcohol, the OH group will always be somewhere in the middle. That is, it could be pentane 2-ol, pentane 3-ol, butane 2-ol. So, if the OH is on the central carbons, then it is a secondary alcohol. Just like in the case of haloalkanes, a tertiary alcohol, the OH bearing carbon will always have an alkyl group. So, 2-methyl pentane 2-ol is a secondary alcohol. 3-methyl pentane 3-ol is a secondary alcohol. 2-methyl pentane 3-ol is a secondary alcohol because the methyl is on the second carbon, whereas the OH is on the third carbon. So, 2-methyl pentane 3-ol is a secondary alcohol, or 3-methyl pentane 2-ol also is a secondary alcohol. 3-methyl hexane 3-ol, tertiary alcohol. So, from the names you can differentiate between whether an alcohol is the primary, secondary or tertiary. Why? Because in many of the questions that you find or in the textbook that you read, you will find the names are given, and from the name you must be able to identify whether it belongs to the primary category, secondary category or the tertiary category. Because whenever we talk about the properties of alcohol, it is easy for us also to add the differentiation between primary alcohol, secondary alcohol, tertiary alcohol. Now, there are certain old names which are very common. Now, in the case of alcohols, methanol is called the simplest alcohol is methanol. Then you got ethanol, then you got propanol. So, all these also have certain old names. You can just list, we can just list out the names and you can find out the names, old names of all. Another thing, there is an alcohol called isopropanol. This is an old name. Isopropanol corresponds to what? Propane 2-ol. Propane 2-ol represents what? Isopropanol. So, isopropyl alcohol. These names will be encountered during the discussion of alcohol. So, you must always remember what is propane 2-ol. So, old name is isopropanol or isopropyl alcohol. Remember that. So, this is the most important thing. Now, isopropanol today, we should be more familiar with isopropanol because isopropanol is the most important ingredient of all our sanitizers. Sanitizers are mainly containing isopropanol with glycerin is the mixture normally used for what? Preparing all our sanitizers. Okay. So, that name you should be able to correlate it with structure. Isopropanol is what? Propane 2-ol. Okay. This is a very interesting thing that you must remember. Now, for example, when you consider propane 1-ol, propane 2-ol, 2-methyl propane 2-ol, we are talking about primary alcohol, secondary alcohol and tertiary alcohols.